There is a galaxy in the observable universe whose diffuse envelope of ancient starlight stretches across 4 million light-years of space. If it were placed where the Milky Way currently sits, it would not merely engulf our galaxy. It would consume every galaxy in our entire local neighborhood, swallowing Andromeda, the large and small Magellanic Clouds, the Triangulum Galaxy, and dozens of smaller satellite galaxies, all of them absorbed into a single structure that still would not have reached its outermost boundary. That galaxy is called IC 1101, and it sits at the center of a massive galaxy cluster over 1 billion light-years from Earth. But here is something that changes the framing of this story almost immediately. IC 1101 might not even be the largest galaxy ever found. Whether it is or is not depends entirely on a question that astronomers have not fully resolved. It depends on what you mean when you use the word galaxy, and the reason that definition matters so much is that the universe, it turns out, produces galactic structures across multiple axes of scale simultaneously, and those axes do not converge on a single answer. To understand why this question is so difficult to close, and why it leads somewhere genuinely surprising, it helps to begin with what we already know is vast. Not with the exotic or the extreme, but with the familiar, with home. Every star you have ever seen with your naked eye belongs to the Milky Way galaxy. Every constellation, every meteor, every planet visible from Earth in the night sky, all of it is part of a single, gravitationally bound structure that spans somewhere between 100,000 and 200,000 light-years, from one edge to the other. That range of uncertainty is itself significant. The difference between those two estimates is 100,000 light-years, which is already an almost incomprehensible distance. But take the conservative number, 100,000 light-years across. A light-year is the distance that light travels in a single year while moving at approximately 286 million kilometers per hour. In 12 months of uninterrupted travel at that speed, a photon covers roughly 9.5 trillion kilometers. Multiply that by 100,000 and you get the diameter of our galaxy. The result is a number so large that writing it out as kilometers produces a string of zeros that stops being emotionally useful almost instantly. But there is a way to feel this scale that bypasses the problem of large numbers entirely. If you fired a beam of light from one edge of the Milky Way toward the other, that beam would not arrive at the far side for 100,000 years. When that photon began its journey, human beings had not yet invented agriculture. By the time it arrived at the other side, we might be unrecognizable as a species, assuming we were still here at all. That is the width of a single average galaxy. The Milky Way contains somewhere between 200 billion and 400 billion stars. Each of those stars is a nuclear furnace powered by the fusion of hydrogen into helium, releasing energy at rates that dwarf anything in human experience. Some of these stars are far more massive than our Sun. Others are far smaller. They are scattered across spiral arms and a central bulge, and a sparse outer halo, their distribution shaped by billions of years of gravitational evolution. Most of them likely host planets. Data from the Kepler Space Telescope and subsequent surveys suggest that planetary companions are the rule rather than the exception, meaning our galaxy alone may contain hundreds of billions of worlds. We have explored one of those worlds in any meaningful sense. There is another fact about the Milky Way that makes its size even harder to process. Despite containing hundreds of billions of stars, the galaxy is overwhelmingly empty. The average distance between neighboring stars in our region of the galaxy is approximately 4 light-years. If you reduce the Sun to the size of a tennis ball, the nearest star at the same scale would be another tennis ball, sitting roughly 1,200 meters away. Everything between them would be a vacuum so complete that a spacecraft traveling through it would encounter functionally 0 atoms per cubic centimeter for most of the journey. The galaxy is not a dense swarm of objects packed tightly together. It is a scattering of tiny luminous points separated by abysses of nothingness so vast that even light requires years to cross them. The galaxy is enormous, not because it is full, but because it must be enormous to contain so much emptiness between its scattered points of light. All that vastness, all those hundreds of billions of stars, all those hundreds of billions of possible worlds, and yet the structure they inhabit is mostly made of nothing. This emptiness has a consequence that reaches beyond aesthetics. Any civilization arising on a planet orbiting one of those stars would be profoundly isolated from every other star in the galaxy. A radio signal sent from Earth toward the nearest stars would take decades to arrive and decades more to return. A spacecraft traveling at any velocity humanity has ever achieved would require tens of thousands of years to make the crossing. The galaxy fills its enormous volume with stars, but the spaces between them enforce a loneliness so deep and so structural that it may be the primary reason we have never detected another civilization among all those hundreds of billions of suns. This is the baseline. This is what we already know is vast before a single comparison has been made. And the Milky Way is not special. Among the estimated 2 trillion or so galaxies in the observable universe, the Milky Way is actually larger than the vast majority. Most galaxies in the cosmos are dwarfs, small, irregular, or elliptical structures containing billions rather than hundreds of billions of stars. The Milky Way is a reasonably massive, barred spiral galaxy with a moderately active history, a supermassive black hole at its center, weighing roughly 4 million times the mass of our Sun, and a set of spiral arms that mark it as a respectable but unremarkable member of the spiral galaxy class. If galaxies were people, the Milky Way would be tall enough to stand out in a crowd, but entirely unremarkable among the other tall figures in the room. And yet, this average galaxy already contains more stars than any human being could count in a lifetime, more potential worlds than there are grains of sand on an entire continent, and more empty space between its stellar points of light than most people can psychologically tolerate thinking about. The average is already extraordinary. What happens when we leave average behind? Look toward the constellation Andromeda on a clear autumn night, and you will find a faint smudge of light that ancient astronomers cataloged as a nebula. That smudge is the Andromeda galaxy, our nearest major galactic neighbor, sitting approximately 2.5 million light-years from Earth. The light reaching your eyes when you look at Andromeda left that galaxy before modern humans existed. You are seeing Andromeda as it appeared when our ancestors were still learning to chip stone tools. And what you are seeing is a galaxy significantly larger than our own. Andromeda spans roughly 220,000 light-years in diameter, which is more than double the conservative estimate for the Milky Way. It contains approximately 1 trillion stars, which is at least 2.5 times and possibly 5 times the number in our galaxy. Its supermassive black hole weighs in at roughly 100 million solar masses, compared to the Milky Way's 4 million. Andromeda is the dominant galaxy in our local group, the gravitational family of more than 80 galaxies that includes both it and the Milky Way as its 2 largest members. For most of human history, we assumed our galaxy was the big one. We were wrong. The 2 galaxies are falling toward each other at roughly 400,000 kilometers per hour. In approximately 4 to 5 billion years, they will collide. Their spiral arms will be destroyed. Their stars will be flung into new orbits. Their supermassive black holes will spiral toward each other, merge, and release gravitational waves detectable across the cosmos. The merger will not destroy individual stars or planetary systems, because the distances between stars are so vast that direct collisions are extraordinarily unlikely. But the galaxies themselves, as structures, will cease to exist in their current form. The 2 trillion stars of both galaxies will be rearranged into a single, massive elliptical object that astronomers have already nicknamed Milky, a name that carries within it the history of 2 great spiral galaxies that once moved through the cosmos independently and now can no longer avoid each other. Now pause and hold what has already been described. The Milky Way spans 100 to 200,000 light-years and contains hundreds of billions of stars. Andromeda spans 220,000 light-years and contains 1 trillion stars. The distance between them is 2.5 million light-years. Together they represent the 2 largest members of our local group, which itself spans roughly 10 million light-years. Everything we know about the universe, every observation we have ever made, every telescope image ever recorded, has been made from inside this system, from a single planet orbiting a single star in the outer arm of the smaller of the 2 dominant galaxies. But even Andromeda, as dominant as it is within our local group, is not close to the upper limit of how large a galaxy can become. Not close. Not even in the same conversation. Andromeda is a large spiral galaxy, but the universe contains galaxies that make spirals look modest by comparison. These are galaxies so enormous that astronomers developed specialized terminology to classify them. They sit at the centers of galaxy clusters like anchors at the bottom of gravitational wells, and they earn their size through billions of years of the most relentless process in galactic evolution. To understand them, you need to understand what a galaxy cluster is and what happens at its center over cosmic time. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds to thousands of individual galaxies, all held together by the combined gravitational pull of visible matter, superheated intergalactic gas, and enormous quantities of dark matter. The Virgo cluster, the nearest major cluster to our local group, contains over 1,300 galaxies and lies roughly 54 million light-years away. Larger clusters contain thousands of galaxies and span tens of millions of light-years. At the center of nearly every large galaxy cluster sits a special type of galaxy that astronomers call a brightest cluster galaxy, or BCG. These sit at the gravitational bottom of the cluster's potential well, the point toward which everything else in the cluster is slowly falling. Over billions of years, smaller galaxies spiral inward through a process called dynamical friction, losing orbital energy and sinking toward the cluster center. When they arrive, the central galaxy absorbs them. It strips their stars, swallows their gas, and incorporates their mass into its own growing body. This process has been happening since the cluster first assembled. In the oldest and most massive clusters, the central galaxy has been feeding for the better part of cosmic history. The result is a category of galaxy classified as a CD galaxy. The lowercase c denotes supergiant. The uppercase D refers to a diffuse stellar envelope, an enormous halo of stars that extends far beyond the galaxy's visible core. These halos do not have sharp edges. They fade gradually into the surrounding space, blending almost imperceptibly into what astronomers call intracluster light, the faint glow of stars that have been gravitationally stripped from their parent galaxies and now drift freely through the cluster's shared gravitational field. Where the galaxy ends and the cluster begins is not always a clean distinction. The CD galaxy has eaten so many neighbors and spread its stars so far that its boundaries become genuinely ambiguous. What distinguishes CD galaxies from ordinary elliptical galaxies is not merely size but structure. A normal giant elliptical follows a brightness profile that decreases smoothly from the center outward. At some radius, the brightness drops below detection thresholds, and the galaxy effectively ends. A CD galaxy follows a similar profile in its inner regions, but at a certain distance from the center, the profile flattens. Instead of continuing to fade, the brightness levels off and extends outward in a diffuse envelope that refuses to end neatly. This extended envelope is the signature of a galaxy built through mergers. Each consumed galaxy adds stars to the outskirts. The envelope is the archaeological record of billions of years of galactic cannibalism, written in starlight that has been accumulating for as long as the cluster has existed. These CD galaxies are the largest visible galaxies in the universe. They are not simply big versions of normal galaxies. They are gravitational end products. They are what happens when one galaxy sits at the bottom of a gravitational well for 10 billion years and eats everything that falls in. Their stellar populations are overwhelmingly old. Their colors are golden, yellow, or red, reflecting the dominance of ancient metal-rich stars that formed billions of years ago in the galaxies that were consumed. They have very little ongoing star formation because the mergers that built them also heated and expelled the gas needed to make new stars. They are enormous, ancient, slowly dimming, and utterly dominant within their clusters. The supermassive black holes at the centers of these galaxies are among the most massive ever discovered. While the Milky Way's central black hole weighs roughly 4 million solar masses, and Andromeda's weighs roughly 100 million, the black holes in CD galaxies can weigh tens of billions of solar masses. These are objects whose event horizons are wider than our entire solar system. Gravitational engines so powerful that they shape the thermal properties of gas across millions of light-years of cluster space during their active phases. Among all CD galaxies ever observed, one has consistently stood out as the most extreme example of visible galactic size. It sits at the center of a galaxy cluster called Abell 2029, located over 1 billion light-years from Earth. Its catalog designation is IC 1101, and its story begins not with modern astronomy, but with a night in the summer of 1790. On the 19th of June, 1790, the astronomer William Herschel pointed his telescope toward a patch of sky near the border of the constellations Virgo and Serpens and recorded a faint smudge of light. He catalogued it, as he did with thousands of other objects during his decades-long survey of the heavens, and moved on. Herschel had no way of understanding what he was looking at. The concept of galaxies as vast external systems of stars separate from our own Milky Way would not be established for another 130 years. To Herschel, the object was simply another nebula, another fuzzy patch among hundreds scattered across the sky. He noted its position, its approximate brightness, and nothing more. The smudge waited. It waited through the entire 19th century, through the development of spectroscopy and the first measurements of stellar distances. It waited through the great debate of the 1920s, when Edwin Hubble proved that certain nebulae were in fact entire galaxies, lying millions of light years beyond the Milky Way. It waited through the construction of ever larger telescopes, through the space age, through the launch of orbiting observatories that could see the universe without atmospheric distortion. And when astronomers finally turned the full power of modern instrumentation toward that faint mark recorded by Herschel more than 2 centuries earlier, what they found was one of the most extreme single objects in the observable universe. IC 1101 is the 1101st entry in the Index Catalog of Nebulae and Clusters of Stars, a supplement to the New General Catalogue, first published in 1895 by the Danish astronomer John Louis Emil Dreyer. The name is bureaucratic, a filing label rather than a title, but the object it refers to is anything but ordinary. IC 1101 sits approximately 1.15 billion light-years from Earth. The light we observe from it today left the galaxy when multicellular life on Earth was still a relatively recent evolutionary development. Everything we know about it, every measurement, every image, every spectrum, describes the galaxy as it appeared over 1 billion years ago. What it looks like now is something we will never know. Measuring the size of a distant galaxy is not straightforward because galaxies do not have hard edges. They fade gradually, from bright cores to dimmer outer regions to halos of diffuse light that eventually blend into the darkness of intergalactic space. Where you draw the line determines the number you get. For IC 1101, the most commonly used scientific measurements give an isophotal diameter, which is the diameter measured at a specific surface brightness threshold of approximately 400,000 to 550,000 light-years. The lower estimate comes from measurements in visible blue light. The higher estimate comes from infrared observations by the 2-micron all-sky survey, which detects older, redder stars that glow more prominently at longer wavelengths. Both numbers are already extraordinary. At 400,000 light-years, IC 1101 is roughly 4 times the diameter of the Milky Way. At 550,000 light-years, it approaches 6 times the diameter. But these measurements only describe the galaxy's brighter stellar body. Beyond that body lies something even more remarkable. Deep imaging observations, particularly those conducted in red light bands, revealed a vast, diffuse stellar halo extending outward from the core to a radius of approximately 2 million light-years. That gives a total halo diameter of roughly 4 million light-years. Let that number sit for a moment before moving on. The Milky Way at its widest spans 200,000 light-years. Andromeda spans 220,000 light-years. The distance between the Milky Way and Andromeda is approximately 2.5 million light-years. If you place the visible stellar body of IC 1101 at the center of our local group, it would extend well beyond the Milky Way in every direction. Its bright inner region alone would engulf our galaxy entirely. Now extend the picture to include the halo. At a radius of 2 million light-years, the diffuse stellar envelope reaches nearly to the distance of Andromeda itself. If IC 1101 were placed at the Milky Way's location, it would engulf Andromeda, the Large Magellanic Cloud, the Small Magellanic Cloud, the Triangulum Galaxy, and nearly every other galaxy in the local group. A single galaxy occupying the space that our entire galactic neighborhood currently fills. Try to feel this in a different way. Imagine you could travel at the speed of light, the absolute fastest anything can move in our universe. Starting at one edge of IC 1101 stellar body and flying toward the other, you would travel for more than 400,000 years before emerging on the far side. If you began that journey when Neanderthals still walked the Earth alongside early modern humans, you would not have arrived yet, and that only crosses the stellar body. To traverse the full halo from one edge to the other, your journey at light speed would take roughly 4 million years. When you began, the genus Homo had barely appeared on the African savanna. By the time you finished, you would have traveled for the entire span of human evolutionary history, and then continued for millions of years beyond it. That is the diameter of a single galaxy's diffuse envelope of light. IC 1101 contains approximately 100 trillion stars. That is a ratio of roughly 250 to 500 times more stars than the Milky Way, and approximately 100 times more than Andromeda's 1 trillion. These are not freshly formed stars blazing blue and hot with recent creation. These are ancient stars, most of them old and slowly cooling, their golden yellow light characteristic of metal-rich stellar populations that formed billions of years ago in the galaxies that were consumed and absorbed. Their starlight is not homegrown. It is inherited from the remains of galaxies that no longer exist as independent objects. The local group is not a small structure. It contains more than 80 galaxies spread across roughly 10 million light-years of space. IC 1101 does not merely compete with the Milky Way for size, it competes with the local group itself. The galaxy at the center of Abell, 2029, is classified as a CD galaxy, placing it in the category of supergiant galaxies built through gravitational assembly at the centers of rich clusters. Its exact shape has been debated. Some classifications describe it as an elliptical galaxy. Others classify it as a lenticular galaxy, a transitional form between spirals and ellipticals that possesses a disc-like structure but lacks spiral arms. What both classifications agree on is that IC 1101 is not a spiral. It does not have the organized rotating disk of stars and gas that characterizes galaxies like the Milky Way and Andromeda. It is a massive, roughly spheroidal collection of old stars that have been gravitationally scrambled by billions of years of mergers. Whatever spiral structures its progenitor galaxies once possessed were destroyed long ago, torn apart and absorbed into the chaotic orbits of the final merged product. To understand the violence of that construction process, consider what a single galactic merger actually looks like. When two large galaxies collide, the event unfolds over hundreds of millions of years. First, the dark matter halos, invisible but gravitationally dominant, begin to interpenetrate. Then, tidal forces stretch both galaxies into distorted shapes, pulling streams of stars into long tails that can extend millions of light years into intergalactic space. Gas clouds in both galaxies compress, triggering violent bursts of star formation. The supermassive black holes, at the centers of both galaxies, spiral inward toward each other, eventually merging in an event that releases gravitational waves propagating outward through space-time. The entire process is chaotic, destructive, and creative simultaneously, forging a new and larger galaxy from the wreckage of two smaller ones. Now imagine that process happening not once, not twice, but dozens or perhaps hundreds of times over the course of 10 billion years. Each merger adds mass. Each merger destroys existing structure and replaces it with a larger, more diffuse configuration. Each merger brings in new stars, new gas, new dark matter, and sometimes a new supermassive black hole that must be absorbed by the existing central engine. The galaxy at the bottom of the gravitational well grows relentlessly, fed by everything that spirals inward from the cluster outskirts. It is not growing through peaceful accumulation. It is growing through repeated acts of gravitational violence, each collision reshaping the galaxy from the inside out. IC 1101 is the end product of that violence. It is the accumulated scar tissue of a billion years of cosmic collisions, smoothed over time into the golden, featureless ball of ancient starlight that telescopes reveal today. At the center of IC 1101 lies a supermassive black hole, whose estimated mass ranks among the highest ever measured. Different calculation methods produce different estimates, but the range spans from roughly 40 billion to 100 billion solar masses. To appreciate what these numbers mean, compare them to the supermassive black hole at the center of the Milky Way, known as Sagittarius A star, which weighs roughly 4 million solar masses. The black hole in IC 1101 outweighs ours by a factor of 10,000 to 25,000. It does not merely belong to a larger category of the same object. It belongs to a completely different class of gravitational engine entirely. A 2017 study using Hubble Space Telescope imaging found that IC 1101 possesses the largest known galactic core of any galaxy observed to date. The core radius measures approximately 14,000 light-years, which is roughly an order of magnitude larger than the cores of other well-studied giant elliptical galaxies. This oversized core is believed to be the result of a process called core scouring, in which merging supermassive black holes during past galactic collisions gravitationally ejected stars from the central region, carving out a vast depleted zone over billions of years. The physics of core scouring is both elegant and violent. When two galaxies merge and their central black holes spiral toward each other, the pair forms a gravitationally bound binary system in the merged galaxy's core. As the binary tightens, it interacts with nearby stars through three-body gravitational scattering. Stars that wander close to the binary are flung outward at high velocity, expelled from the core like projectiles from a slingshot. Each ejection removes mass from the central region and transfers energy to the remaining stars, causing them to spread outward. Over millions of years, this process excavates a cavity in the galaxy's center, creating the diffuse, depleted core that observations reveal. For IC 1101, the mass deficit in the core, meaning the amount of stellar mass that has been ejected by this process, has been estimated at roughly 490 billion solar masses. The total stellar mass of the Milky Way is estimated at roughly 50 to 60 billion solar masses. IC 1101 has thrown away more stars from its center than the entire Milky Way contains in total. These ejected stars did not vanish. They were scattered into the outer halo and into the surrounding cluster, contributing to the diffuse envelope of light that extends millions of light years from the core. The halo of IC 1101 is partly built from the debris of its own internal violence, stars exiled from the center by the gravitational dynamics of merging black holes. IC 1101 is not forming new stars in any significant quantity. It is, in the terminology astronomers sometimes use, a dying galaxy. The mergers that built it also heated and expelled the gas needed for star formation. There are no glowing nebulae, no stellar nurseries, no blue supergiant stars blazing with the energy of recent creation. IC 1101 glows with the steady, fading light of ancient stars, a monument to a violent past that has now grown quiet. If galaxies had seasons, this one would be deep in autumn, with winter approaching slowly over the next billions of years as its oldest stars exhaust their nuclear fuel one by one. The galaxy's environment reinforces its dominance. Abell 2029 is one of the densest galaxy clusters in the sky, containing thousands of galaxies, including hundreds of giant members. Yet IC 1101 alone accounts for roughly a quarter of the entire cluster's visible light output. A single galaxy producing 1/4 of the luminosity of a structure containing thousands of galaxies. The cluster itself is enveloped in an enormous cloud of superheated gas that glows in X-ray wavelengths, reaching temperatures of roughly 100 million degrees Celsius. IC 1101 sits at the very center of this hot gas cloud, at the deepest point of the cluster's gravitational potential. Well, exactly where physics predicts the most massive galaxies should reside. The history of how IC 1101 reached this size is written in the properties of its halo. Studies of brightest cluster galaxies in general suggest that these objects assembled roughly half of their mass through mergers that occurred more than 8 billion years ago, with subsequent growth proceeding more slowly as the rate of galactic infall decreased. IC 1101 likely consumed dozens of major galaxies and hundreds of smaller ones over its lifetime. Each collision added to its mass, expanded its halo, and fed its central black hole. Think about what that means concretely. Every major galaxy that fell into the center of Abell 2029 over the past 10 billion years was absorbed into IC 1101. Galaxies that may have been comparable in size to the Milky Way. Galaxies that may have contained their own planetary systems, their own chemistry, perhaps even their own biology. All of them consumed. All of their stars now orbiting within the body of a single vast, slowly dimming giant. The galaxy is not just large. It is a graveyard, a monument built from the remains of everything that wandered too close to the center of the cluster over cosmic time. This connects uncomfortably to something closer to home. Earlier, we described how the Milky Way and Andromeda are falling toward each other and will merge in roughly 4 to 5 billion years, producing a single massive elliptical galaxy containing the combined stellar populations of both. That merged galaxy, Milky, will be large by the standards of our local neighborhood, perhaps over 1 trillion stars, a respectable elliptical with a substantial dark matter halo and a merged supermassive black hole. It will be the dominant galaxy in what remains of the local group. And for a moment, it might feel like the end of the story. But IC 1101 reveals that Milky would not be the end of anything. It would be the beginning. Because IC 1101 was built from exactly this kind of merger, repeated over and over across billions of years, every galaxy that fell into the center of Abell, 2029, was at some point the product of its own previous mergers. Spiral galaxies collided with other spirals to form ellipticals. Ellipticals consumed dwarfs. The resulting objects fell deeper into the cluster potential well and were absorbed by the growing central giant. The process is hierarchical, recursive, and relentless. If the Milky Way and Andromeda happened to sit at the center of a massive galaxy cluster instead of in the relatively sparse local group, their merger product would not be a final form. It would be an appetizer, a single course and a meal that lasts for 10 billion years. Milky, the galaxy that would one day contain every star and planet we have ever known, would be a minor contribution to IC 1101's total mass. Its trillion stars would be absorbed, scattered, and redistributed within a few 100 million years. Nothing about Milky, not its structure, not its history, not whatever civilizations might still exist within it, would survive as a recognizable feature. The product of the Milky Way and Andromeda's cosmic collision would vanish into the body of the larger galaxy like a raindrop falling into a lake. Now here is where the framing of this story becomes important, because the way IC 1101 has been described in popular media over the past 2 decades has not always been scientifically precise. Many sources claim that IC 1101 has a diameter of 6 million light-years, making it the largest galaxy in the universe by a wide margin. This figure appears on dozens of websites, in popular science articles, and in videos. But if you trace it back to primary scientific literature, it becomes difficult to find a well-sourced origin. The 6 million light-year number likely comes from including the most extended, faintest reaches of the galaxy's halo, and possibly conflating it with intracluster light, which are stars that have been stripped from their parent galaxies and now drift freely through the cluster. Those stars are gravitationally associated with IC 1101, but arguably they belong to the cluster as a whole rather than to the galaxy itself. Determining which stars belong to the galaxy and which belong to the cluster requires careful dynamical modeling, and different assumptions produce different answers. The galaxy size is not uncertain because astronomers have been sloppy. It is uncertain because the galaxy itself does not have a clean physical boundary. It blurs into its surroundings in a way that makes the question of where the galaxy ends genuinely difficult to answer. But what is not uncertain is the galaxy's position at the extreme end of the size distribution for visible galaxies. Even at the lower estimates, IC 1101 is among the largest stellar bodies ever observed, with a halo among the most extensive ever measured, and a core that is the largest ever detected. But the word visible in that sentence is doing critical work. It opens the door to the next chapter of this story, because IC 1101 is enormous by any standard applied to the stellar body of a galaxy. But the universe does not restrict galactic structures to what human eyes or optical telescopes can see. There are galaxies in the cosmos whose influence extends far beyond their stellar bodies, far beyond their halos, far beyond anything that emits light in the wavelengths we associate with stars and gas. And when you measure those galaxies, not by their visible extent, but by the full reach of their physical structures, the question of which galaxy is largest becomes considerably more complicated. To understand why, you need to understand what happens at the center of a galaxy when its supermassive black hole is actively consuming material. At the center of certain galaxies, the supermassive black hole draws in surrounding gas and dust, forming a rapidly spinning accretion disk. This disk is not a calm or orderly structure. It is a superheated maelstrom of plasma, spiraling inward at velocities approaching a significant fraction of the speed of light, compressed by gravitational forces so intense that the inner regions reach temperatures of hundreds of millions of degrees. Friction within the disk converts gravitational potential energy into radiation. At the peak of its activity, the accretion disk around a supermassive black hole can outshine the entire galaxy that hosts it. But not all of the infalling material reaches the black hole's event horizon. A fraction of it, channeled by powerful magnetic fields threading the accretion disk and the spinning black hole's ergosphere, gets launched outward along the black hole's rotational axis in two tightly collimated beams called relativistic jets. These jets travel at velocities approaching the speed of light, sometimes exceeding 99% of it. They are among the most energetic phenomena in the universe, carrying the power output equivalent to trillions of suns in two narrow beams that punch through the galaxy's interstellar medium and continue outward into intergalactic space. As the jets interact with the surrounding gas, they slow down, spread out, and inflate enormous lobes of magnetized plasma. These lobes grow over millions of years, fed continuously by the jets, expanding outward until the pressure of the surrounding intergalactic medium balances the energy being pumped into them. The electrons in the lobes spiral around the magnetic field lines at relativistic speeds, emitting what is called synchrotron radiation that peaks at radio wavelengths. This radiation is how astronomers detect the lobes, which are otherwise invisible to optical telescopes. The lobes glow only in radio light, ghostly structures spanning distances that can dwarf the visible galaxy at their center. Most radio galaxies produce lobes that extend a few 100,000 light-years from the central galaxy. Impressive, but comparable in scale to the galaxy's own stellar body. Even the Milky Way has its own pair of modest radio lobes, detected in recent years extending above and below the galactic plane. These structures are a normal part of galactic astrophysics, a consequence of black hole activity that most large galaxies experience at some point in their evolution. But there is a subset of radio galaxies that defies this modest scaling. Astronomers call them giant radio galaxies, and their defining characteristic is that their radio lobes extend to truly extraordinary distances, reaching lengths measured not in hundreds of thousands of light-years, but in millions. Some span several megaparsecs, where 1 megaparsec equals roughly 3.26 million light-years. These structures do not merely extend beyond their host galaxy. They extend beyond the galaxy's local environment, beyond the scale of galaxy groups, into the spaces between cosmic web filaments. And the discoveries that changed the conversation about the largest galaxy in the observable universe came in rapid succession beginning in 2022. In February of 2022, a team of astronomers led by Martijn Owe at the Leiden Observatory in the Netherlands published a paper announcing the discovery of a giant radio galaxy they named Alcyoneus, after one of the giants of Greek mythology. The galaxy was identified in data from the Low Frequency Array, known as LOFAR, a network of roughly 20,000 individual radio antennas distributed across 52 stations in Europe. LOFAR operates at frequencies far below what optical telescopes detect, and its sensitivity to faint diffuse radio emission makes it ideally suited for detecting the extended lobes of giant radio galaxies. What Owe and his colleagues found was remarkable. Alcyoneus possessed a radio structure spanning approximately 5 megaparsecs in projected length, which translates to roughly 16 million light-years from one lobe edge to the other. To place that in context, the Milky Way is approximately 100,000 to 200,000 light-years across. Alcyoneus's radio structure was roughly 100 times the diameter of the Milky Way. If you laid 100 Milky Way galaxies end to end, the chain would match the span of this single radio structure. At the time of its discovery, it was the largest known structure of galactic origin ever detected. But the media response that followed obscured a critical distinction. Headlines declared Alcyoneus the largest galaxy in the universe. But the framing was misleading because the host galaxy at the center of Alcyoneus's radio structure, the actual stellar body, is not exceptional at all. Its stellar mass is estimated at roughly 240 billion solar masses, which is only a few times that of the Milky Way, and far smaller than the 100 trillion stars of IC 1101. Its central supermassive black hole weighs approximately 390 million solar masses, a respectable but entirely ordinary mass for an elliptical galaxy, and roughly 100 to 250 times less massive than the black hole in IC 1101. By every measure of the visible stellar body, the host galaxy of Alcyoneus is unremarkable. It is an ordinary elliptical galaxy embedded in a filament of the cosmic web, indistinguishable from thousands of similar objects scattered throughout the observable universe. What makes Alcyoneus extraordinary is not its galaxy, it is its jets. The two enormous lobes of magnetized plasma, extending millions of light-years in opposite directions from the central black hole, inflated over millions of years by relativistic outflows that have been pumping energy into intergalactic space. These lobes are not made of stars. They contain no planets, no solid matter, no structure that would be recognizable as galactic in the traditional sense. They are tenuous, diffuse clouds of plasma so thin that their internal pressures rank among the lowest ever measured in any astrophysical structure. They glow only in radio wavelengths, invisible to any optical telescope ever built. The mismatch between cause and effect is almost conceptually disorienting. The engine is ordinary. The output is colossal. Strip away the radio lobes from Alcyonius, and you are left with a galaxy that no survey would flag as unusual. Restore them, and you are looking at a structure 100 times wider than the Milky Way. Something about the environment in which Alcyonius sits, specifically the unusually low density of the surrounding intergalactic medium in that region of the cosmic web, allowed the lobes to expand with minimal resistance, growing to a scale that an equally powerful black hole in a denser environment might never achieve. But even as astronomers were processing the implications of Alcyonius, the record was already being broken. In September of 2024, a paper published in the journal Nature by a team again led by OE announced the discovery of an even larger giant radio galaxy. This one was named Porphyrion, after another giant of Greek mythology, and its scale made Alcyonius look modest by comparison. Porphyrion's radio jets span approximately 7 megaparsecs, or roughly 23 million light-years from end to end. That is approximately 140 times the diameter of the Milky Way. If you could somehow visualize Porphyrion's full extent, the two plasma lobes would span a distance that makes even IC 1100 and one's 4 million light-year halo look contained and local. The host galaxy of Porphyrion lies 7.5 billion light-years from Earth, meaning the jets existed when the universe was only 6.3 billion years old, less than half its current age. Despite its extreme youth in cosmic terms, the central black hole generated jets with a combined power output equivalent to the energy of trillions of suns, punching plasma into intergalactic space at nearly the speed of light, and inflating lobes that stretched across a volume of space, comparable in scale to the gaps between filaments of the cosmic web. The research team calculated that Porphyrion's jets span roughly 2/3 the radius of a typical cosmic void at that epoch of universal history. This is not a comparison between a galaxy and other galaxies. This is a comparison between a galaxy's output and the large-scale structure of the universe itself. The jets were threading through the cosmic web, potentially magnetizing the intergalactic medium, heating the gas between filaments, and influencing the formation and evolution of other galaxies located millions of light-years from the source. OE and his colleagues wrote that their findings suggest supermassive black holes do not only hold sway over their immediate galaxy, but over the cosmic web that surrounds them. This is not a minor addendum. It is a fundamental reframing of what a galaxy's influence can mean. For years, one of the persistent puzzles in astrophysics has been the origin of magnetic fields in the intergalactic medium. Observations confirmed that the gas between galaxies is permeated by weak but measurable magnetic fields, but the mechanism that produced them was debated. One leading hypothesis proposes that magnetic fields arise naturally from the differential motion of electrons and ions under gravitational forces. But this mechanism produces extremely weak seed fields that would need substantial amplification by other processes to match observed strengths. Giant radio galaxy jets offer an alternative and potentially more powerful explanation. If jets spanning tens of millions of light-years routinely inject magnetized plasma into the intergalactic medium, they could be a primary source of cosmic magnetism on the largest scales. Porphyrion's discovery strengthened this hypothesis by demonstrating that jet structures can reach sizes comparable to the cosmic web itself. And even Porphyrion's record did not last. By late 2024, another radio galaxy, designated TXS 0033 plus 252, was identified with an estimated radio structure spanning approximately 8 megaparsecs, or roughly 26 million light-years, surpassing Porphyrion. Another record broken before the previous one had been fully absorbed by the scientific community. Now lay these out in sequence and consider what the progression reveals. The Milky Way spans 100,000 to 200,000 light-years. Andromeda spans 220,000 light-years. IC 1101's visible stellar body spans 400,000 to 550,000 light-years. IC 1101's full halo spans approximately 4 million light-years. Alcyonius's full radio structure spans approximately 16 million light-years. Porphyrion's full radio structure spans approximately 23 million light-years. TXS 003 3 plus 252 spans approximately 26 million light-years. Each step on that ladder does not merely increase the number, it changes the category. The jump from the Milky Way to Andromeda is a jump within the same class of objects. The jump from Andromeda to IC 1101 is a jump from a large spiral to a supergiant elliptical, built through fundamentally different processes. The jump from IC 1101's stellar body to its halo is a jump from the galaxy's bright interior to its fading gravitational periphery, where the boundary between galaxy and cluster becomes ambiguous. And the jump from IC 1101's halo to the radio structures of Alcyonius and Porphyrion is a jump from assembled starlight to relativistic plasma, from gravitational architecture to energetic outflow, from the galaxy as a collection of stars to the galaxy as a source of influence that extends across cosmological distances. At each step, the previous reference point shrinks. The Milky Way, which seemed impossibly vast at the beginning, becomes a rounding error by the time you reach IC 1101. IC 1101, which seemed like the ultimate expression of galactic scale, becomes a dot at the center of Porphyrion's radio structure. The comparisons that were designed to make you feel the scale stop producing the emotional response they were built for. The numbers become too large. The gaps between the rungs become too wide. The ladder climbs past the altitude where human intuition can breathe. This is not a problem with the science. It is a feature of the universe. If a LOFAR survey has already surveyed only about 15% of the northern sky and has already identified more than 10,000 jet pairs spanning roughly 3 million light-years or more, the population of giant radio galaxies is not a collection of rare curiosities. They are a class of objects that the universe produces routinely, and their typical scales dwarf anything measured in visible starlight. A citizen science effort associated with LOFAR surveys has already confirmed this abundance. The records keep falling not because we are approaching a maximum, but because each new survey reveals that the maximum is further away than previously assumed. There is no theoretical ceiling that says radio jets cannot extend beyond 30 million light-years, or 40, or 50. The limiting factor appears to be the density of the intergalactic medium, which varies from region to region across the cosmic web. In denser environments, jets are confined and cannot grow as large. In sparser environments, in the voids between filaments where the intergalactic medium is thinnest, jets can expand with minimal resistance. If there exists somewhere in the unobserved universe a supermassive black hole embedded in a galaxy sitting in an unusually sparse region of the cosmic web, with just the right accretion rate and just the right jet orientation, its radio structure could potentially extend to scales we have not yet observed. LOFAR has so far mapped only 15% of the northern sky. The full survey, when complete, will cover the entire northern hemisphere at sensitivities that exceed earlier radio surveys. Every previous expansion of LOFAR coverage has revealed new giant structures and new record holders. There is no reason to expect this trend to stop. The remaining 85% of the northern sky almost certainly contains giant radio galaxies that surpass everything currently known, and LOFAR itself will eventually be surpassed. The Square Kilometre Array, an international radio telescope project currently under construction across sites in South Africa and Australia, will be the most sensitive radio telescope ever built when completed. With a total collecting area of approximately 1 square kilometer and a sensitivity that exceeds LOFAR by an order of magnitude, the SKA will survey the entire sky at frequencies and resolutions that make current instruments look preliminary. It will detect radio lobes so faint and so extended that they are invisible to every existing telescope. If giant radio galaxies are as common as LOFAR's partial survey suggest, the Square Kilometre Array will discover them in the hundreds of thousands, revealing for the first time the true statistical distribution of the largest galactic structures in existence. What that distribution looks like is one of the most consequential unknowns in extragalactic astronomy. If it has a sharp cutoff, a maximum scale beyond which jets simply cannot grow, then the current records are close to the physical limit. If it has a long tail, extending to sizes significantly larger than anything yet observed, then the universe contains structures of galactic origin that we have not yet imagined. This is what separates this story from a simple exercise in large numbers. It is not just that the largest galaxies are large. It is that the concept of largest resists closure. So which galaxy is actually the largest? The answer depends on what you measure. If you define a galaxy by its visible stellar body, the extent of its stars, and the light they produce, then IC 1101 remains one of the strongest candidates. Its isophotal diameter of 400,000 to 550,000 light-years, combined with a diffuse stellar halo extending to roughly 4 million light-years, places it at or near the top of every observed distribution of visible galactic size. In the category of visible galactic scale, IC 1101 is the anchor. But if you define a galaxy by the total extent of any coherent physical structure connected to its central engine, including radial lobes inflated by relativistic jets, then the record belongs to objects like Porphyrion and its successors. Their physical extents of 23 to 26 million light-years exceed the halo of IC 1101 by factors of roughly 6 to 7. They reach distances that place them in a different category entirely, structures that span not just galactic scales but cosmological ones. The tension between these two definitions is not a flaw in astronomy. It is a reflection of genuine physical reality. Galaxies are not simple objects. They are multi-layered systems with stellar bodies, dark matter halos, gas reservoirs, magnetic fields, and in some cases, relativistic outflows that extend far beyond anything the stars alone could reach. An astronomer studying stellar populations might define galaxy size by the extent of the stars and conclude that IC 1101 is the largest. A radio astronomer studying jet physics might define galaxy size by the extent of the radio structure and conclude that Porphyrion holds the record. Both are correct within their frameworks. Neither is wrong. The universe simply does not provide a single unambiguous answer. Now consider what this means for our understanding of what a galaxy actually is. For most of the history of astronomy, galaxies were treated as discrete objects, islands of stars separated by vast empty spaces. The space between galaxies was considered largely inert, populated only by sparse intergalactic gas and the invisible scaffolding of dark matter. Galaxies were the actors. The space between them was the stage. But giant radio galaxies dissolve this distinction. When a single galaxy's jets span 23 million light-years, threading through the cosmic web, magnetizing the intergalactic medium, heating gas in neighboring filaments, the galaxy is no longer confined to its own island. Its influence has leaked out, contaminated the space between structures, blurred the boundary between actor and stage. A galaxy is supposed to be a bounded object, a collection of stars and gas and dark matter held together by gravity, distinct from its surroundings, definable, measurable. But when a galaxy's radio lobes extend 23 million light-years into intergalactic space, is the structure still a galaxy? When a galaxy's stellar halo merges imperceptibly into the intercluster light of its parent cluster, where does the galaxy end and the cluster begin? When a galaxy's jets magnetize the cosmic web across scales rivaling the distances between filaments, is the galaxy's influence truly local? These are not rhetorical questions. They are active areas of research, and the answers, when they come, will likely reveal that the boundaries we draw around galaxies are human constructs imposed on a cosmos that does not recognize them. The universe builds structures continuously, from stellar scales, to galactic scales, to cluster scales, to cosmic web scales. The transitions between them are not sharp. They are gradients, zones of diminishing influence that fade rather than end. A galaxy is not a thing with an edge. It is a concentration of matter and energy at the center of a zone of influence that extends, in principle, indefinitely outward. Now consider the Milky Way in the context of everything described. Our galaxy's radio lobes are small by the standards of giant radio galaxies. Its influence extends in stellar terms only a few 100,000 light-years. In the context of the cosmic web, the Milky Way is a single node in a filament, gravitationally bound to a small group of neighbors, falling slowly toward the Virgo cluster, along with the rest of the Laniakea supercluster. Our galaxy's contribution to the large-scale structure of the universe is negligible, but the Milky Way's insignificance at these scales goes deeper than mere size. It is structural. At the scale of Porphyrion's jets, our galaxy is not merely small, it is undetectable. Porphyrion spans 23 million light-years. The Milky Way spans 200,000 light-years. The ratio is roughly 115 to 1. If Porphyrion's radio structure were scaled to the length of a football field, the Milky Way would span barely a single yard of the total distance. Our entire galaxy, with all its stars, all its planets, all its possible civilizations, reduced to a single stride on a playing surface you could cross in a minute. You would need that full minute to walk from one end of the field to the other. Our galaxy would occupy one step somewhere in the middle, This is not a poetic exaggeration. It is a direct consequence of the measurements. Every observation humanity has ever made of the cosmos has been made from inside the Milky Way. Every telescope, every space probe, every photon we have ever collected has arrived at instruments located within our galaxy. Our entire understanding of the universe is built on observations made from a platform that, at the scales we have been discussing, barely qualifies as a location. We are observing the cosmos from a pixel, a single unremarkable pixel in a structure so vast that the structure itself is unremarkable compared to what the universe can build. And here's the perspective that makes the whole picture snap into focus. Every astronomy textbook, every map of the cosmic web, every diagram of the observable universe, all of them place the Milky Way at the center, because that is where the observer is located. But the centrality is observational, not physical. There is nothing special about our position. There is nothing special about our galaxy, or the filament we inhabit, or the supercluster we belong to. We are an average galaxy in an average location. The only reason the universe appears to radiate outward from us is that light takes time to travel, creating a spherical observational horizon centered on wherever the observer happens to stand. An observer in IC 1101 would see a different observable universe centered on a different point. An observer in Porphyrion's host galaxy would see yet another. Every location in the cosmos is the center of its own observational sphere, and none of them is privileged. IC 1101, sitting at the center of Abell 2029, shapes the thermal properties of its entire cluster. Its black hole's past activity influenced gas dynamics across millions of light years. Its gravitational dominance accreted material from the cosmic web along the axis, connecting its cluster to the neighboring Abell 2033. It is not merely embedded in the cosmic web. It has consumed enough of its local web to become the dominant feature of its own cosmic neighborhood. And Porphyrion, with its jets reaching 2/3 the radius of a cosmic void, does not merely sit in the web, it reaches across the web. Its outflows interact with the intergalactic medium on scales that rival the voids themselves. A single galaxy's black hole pumping energy into space equivalent to trillions of suns, sculpting the magnetic field of the cosmos across distances that dwarf everything we have ever called large. The galaxy does not merely occupy a position in the cosmic web. It modifies the web. It reaches across the voids. It touches other filaments. It injects energy, magnetism, and heat into regions that were supposed to be empty and inert. And at the extreme end of the scale distribution, the distinction between a galaxy and a cosmic structure begins to dissolve. The Milky Way is enormous. Andromeda is larger. IC 1101 is vastly larger still, and the giant radio galaxies extend to scales that make even IC 1101 feel contained and local. Each comparison removes the emotional weight of the one before it. Each new rung on the ladder diminishes everything below it, and the ladder, as far as we can tell, has no visible top. There is a particular kind of disorientation that arrives when you follow this progression all the way up. It is not the same as the awe you feel looking at a photograph of a galaxy. That awe is comfortable, easily held. It is the disorientation of realizing that the cosmos has no obligation to remain within the boundaries of your imagination. You can build a mental model of the Milky Way. You can hold it in your mind as an image, a concept, a thing with a shape and a size. You can do the same for Andromeda with effort. You can even do it for IC 1101 if you anchor it to the comparison with the local group. But you cannot hold Porphyrion in the same way. You cannot visualize 23 million light-years of relativistic plasma extending from a single point source into the void between cosmic web filaments. The image does not fit. The frame of reference does not exist in human experience. The structure is real, measured, confirmed, but it exists beyond the threshold of what our cognitive architecture can render as a picture. And that failure of visualization is not a weakness of science communication. It is the point. The universe at these scales is not supposed to make intuitive sense. It was not built for human comprehension. It was built by gravity, by thermodynamics, by the relentless physics of accretion and ejection operating over billions of years, without any awareness that a species on a small planet in a minor spiral arm would one day try to picture what it had done. The structures exist whether or not we can imagine them. The lobes expand whether or not we can feel their size. The galaxies grow whether or not we have words adequate to describe them. The terrifying size of the largest galaxy we have ever found is not a single number. It is a spectrum. At one end sits IC 1101, the anchor, the visible giant, the most extreme expression of assembled starlight ever observed. A galaxy whose stellar body and halo span millions of light years, and whose black hole ranks among the most massive objects in the cosmos. At the other end sit the giant radio galaxies, Alcyonius and Porphyrion, and the unnamed structures still waiting to be detected in the unobserved sky, whose physical extents reach tens of millions of light years, and whose influence extends to the architecture of the cosmic web itself. Between these two endpoints lies the ambiguity of definition, the honest acknowledgement that largest depends on what you measure, and that the universe refuses to provide a single, clean answer. But the ambiguity does not weaken the story, it deepens it. Because the truly striking realization is not that one specific galaxy is big, it is that the universe can produce galactic structures so vast, across so many different axes of measurement, that even the galaxies we already treat as immense, the Milky Way, and Andromeda, and Messier, 87, and every other galaxy we have ever photographed and studied, begin to look local, begin to look small, begin to look like details in a picture whose full extent we have not yet seen, and may never fully see. The Milky Way is not a large galaxy. It is a speck orbiting inside a supercluster that is itself a minor feature of the cosmic web. Andromeda is not a giant. It is one island among 2 trillion in an observable universe that may represent less than 1% of total cosmic volume. And even IC 1101, the most visually extreme galaxy ever measured, sits at the center of one cluster in one filament of a web that stretches across 93 billion light years of observable space and likely extends far beyond. The largest galaxy we have ever found is not a settled answer. It is a question that keeps expanding, just like the structures it describes. The records will keep falling. The instruments will keep improving. The 85% of the sky that LOFAR has not yet surveyed will yield structures that surpass everything in current catalogs. The square kilometer array will peer deeper into the radio universe than any instrument before it, mapping populations of giant jets that are currently invisible to us. And each new discovery will push the upper end of the distribution further outward, further from human intuition, further from any framework that allows us to feel the scale rather than merely calculate it. What astronomers do know is that the largest galaxy ever found is not an outlier in a universe of ordinary objects. It is the visible edge of a distribution whose true extent has not yet been mapped. IC 1101 represents the extreme of gravitational assembly, the largest visible pile of stars the universe has built through billions of years of mergers and accretion. The giant radio galaxies represent the extreme of energetic reach, the farthest extent any single galactic engine has been observed to influence the cosmos. Both kinds of extreme exist simultaneously. The universe can build galaxies as visually massive as IC 1101 and simultaneously produce single-source structures as physically extended as Porphyrion. And the instruments that will reveal what lies beyond both of these records are already under construction. The largest galaxy we have ever found may not be the largest galaxy that exists, and that possibility is not unsettling in a frightening sense. It is unsettling in the way that the best scientific questions always are, by revealing that the universe is more expansive and more creative than any framework we have built to contain it. Galaxies can become so large, and their influence can extend so far, that the distinction between a galaxy and a cosmic structure begins to blur. A galaxy is supposed to be a bounded object, a collection of matter held together by gravity. But at the extreme end of the scale, the boundary between a galaxy and the universe it inhabits stops being a clean line and starts being a gradient, a slow fade from dense to diffuse, from local to cosmological, from a thing that is part of the universe to a thing that shapes it. That is the scientific picture as it currently stands. IC 1101 anchors the visible end of galactic scale with its 100 trillion stars and its 4 million light-year halo. Porphyrion and its successors define the outer edge of what a single galactic engine can reach in terms of physical extent. Between them, and beyond them, the universe continues to build. Thanks for watching till the end. We'll see you in the next one. To fully appreciate what the existence of these structures means, it helps to step back further and consider the broader cosmic architecture within which they sit. Because IC 1101 and Porphyrion and Alcyonius are not isolated phenomena, They are extreme expressions of processes that operate at every scale in the universe, from the smallest galaxy clusters to the grand filamentary web that gives the cosmos its overall structure. The universe we observe today did not begin as a structured place. In its earliest moments, following the Big Bang approximately 13.8 billion years ago, the cosmos was a nearly uniform sea of hot plasma, in which matter was distributed almost perfectly evenly. The word almost is doing enormous work in that sentence. Because embedded in that near uniformity were tiny quantum fluctuations, regions of slightly higher and slightly lower density imprinted on the fabric of space-time during a period of exponential expansion called inflation that occurred in the universe's first fraction of a second. These fluctuations were extraordinarily small. The differences in density between overdense and underdense regions amounted to variations of roughly 1 part in 100,000. If you were to represent the entire early universe as a perfectly smooth table, the overdense regions would be bumps barely thicker than a coat of paint. And yet, these infinitesimally small variations in the density of the early cosmos are the direct ancestors of every galaxy, every cluster, every filament, and every cosmic void we observe today. Over hundreds of millions of years, gravity amplified these tiny differences. Overdense regions pulled in surrounding matter through their slightly stronger gravitational attraction. As more matter gathered, the gravitational pull grew stronger, drawing in still more matter in a self-reinforcing feedback loop. Underdense regions, lacking sufficient gravity to hold their contents, gradually emptied as their matter flowed outward toward the growing overdense concentrations. The smooth early universe developed structure, and that structure organized itself on a hierarchy of scales. The first structures to collapse and form were the smallest overdensities, dark matter, which does not interact with radiation and could therefore begin clumping together earlier than ordinary matter, formed the first gravitationally bound halos. These dark matter halos provided the gravitational scaffolding into which ordinary gas could fall and cool and condense into the first stars and the first galaxies. The earliest galaxies were small, irregular, and extremely active, producing stars at rates that would be considered extraordinary by modern standards. As cosmic time passed, these small early galaxies were themselves pulled together by gravity into larger structures. Galaxy groups formed from the mergers of smaller associations. Galaxy clusters assembled from the mergers of groups, and at the largest scales, the clusters themselves arranged along filaments of dark matter that connected them into the vast three-dimensional network astronomers call the cosmic web. The cosmic web is the largest structure in the observable universe. It consists of a network of filaments, roughly cylindrical concentrations of matter, that thread through space, connecting galaxy clusters at their intersections, enclosing enormous regions called voids, where matter is extraordinarily sparse. From a sufficiently distant perspective, the cosmic web would look something like a three-dimensional foam or sponge, with dense, interconnected walls and filaments surrounding vast, empty interior spaces. The clusters sit at the nodes where multiple filaments intersect, and they are the densest, most gravitationally active environments in the observable universe. The largest known structure in the cosmic web is the Hercules Corona Borealis Great Wall, a massive concentration of galaxies and galaxy clusters spanning approximately 10 billion light-years. To put that in context, the entire observable universe spans about 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall represents roughly a tenth of the total observable volume. It is not a single gravitationally bound structure, but a concentration in the distribution of matter at cosmic scales, a ridge in the topography of the universe. Our own location within this web is instructive. The Milky Way is a member of the Local Group, which sits in an outer filament of the Virgo supercluster. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii mapped the boundaries of the supercluster that contains our galaxy and gave it the name Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans approximately 500 million light-years and contains the mass of roughly 100 million billion suns, or approximately 100 quadrillion solar masses. It includes more than 100,000 galaxies, of which the Milky Way is one small and entirely unremarkable member. But even Laniakea is not a gravitationally bound structure in the way that a galaxy or a galaxy cluster is. The outer regions of Laniakea are currently expanding away from its center under the influence of the universe's accelerating expansion, driven by the repulsive energy that cosmologists call dark energy. Only the inner regions, falling toward the Virgo cluster at the Laniakea's core, are gravitationally bound and will eventually merge together. The Milky Way itself is not falling toward the Virgo cluster quickly enough to be part of the bound region. We are on the outer margins of our supercluster, moving away from its center at velocities that exceed the gravitational pull trying to draw us back. This means that on a timescale of tens of billions of years, the cosmic web itself will gradually dissolve. The universe's accelerating expansion, driven by dark energy, is steadily increasing the distance between unbound structures. Galaxy clusters, which are gravitationally bound, will survive. Their individual galaxies will continue merging and assembling into ever larger structures within the cluster. But the filaments connecting clusters will eventually thin and disperse as the matter within them is stretched across ever greater distances. In the very far future, each gravitationally bound cluster will become an island, isolated from all other clusters by distances so vast that light traveling between them will never bridge the gap. IC 1101, sitting at the center of Able 2029, will outlast this transition. As the filaments of the cosmic web dissolve and the clusters become isolated islands, IC 1101 will continue growing, consuming whatever remains of the Abell 2029 cluster around it. It will become the final repository of the gravitational potential energy of its entire cluster, and it will keep growing, slowly, as its most distant stellar members gradually cool and dim, as its remaining star-forming gas is exhausted, as its black hole enters an increasingly quiescent phase, but it will persist long after the filaments of the cosmic web have gone dark, long after the nearest cluster has receded beyond the cosmological horizon. IC 1101 will remain, a golden ellipsoid of ancient stellar ash, drifting through an increasingly empty universe. To appreciate the timescales involved, consider the future of the cosmos as physicists currently understand it. The universe is approximately 13.8 billion years old today. Stellar evolution will continue for roughly 100 trillion years, the estimated main sequence lifetime of the smallest, most fuel-efficient red dwarf stars. After that, no new stars will form, and the existing ones will gradually cool and go dark. Between 100 trillion and 100 billion trillion years from now, the remaining stellar remnants, white dwarfs, neutron stars, and black holes will slowly lose orbital energy through gravitational wave emission and infall toward the supermassive black holes at the centers of their host galaxies. The black holes themselves will eventually evaporate through Hawking radiation over timescales so incomprehensibly long that the number of years required to describe them has more digits than there are atoms in the observable universe. IC 1101's central black hole, weighing somewhere between 40 billion and 100 billion solar masses, will be among the last objects in the universe to evaporate. And in the deep future, when the last remnants of its stars have long since been swallowed by that black hole, and the universe has expanded to a cold, dark, near-empty expanse, the black hole itself will quietly radiate away its mass over an almost unimaginable span of time, emitting a trickle of Hawking radiation until nothing remains. But we are getting very far ahead of the story. Return to the present, to the observable universe as it exists today, and consider the populations of galaxies within it and what the distribution of their sizes tells us about the physics that produce them. The vast majority of the estimated 2 trillion galaxies in the observable universe are dwarfs. Tiny, irregular, low-mass systems containing millions to billions of stars without the grand spiral structure of the Milky Way or the massive elliptical bulk of IC 1101. These dwarf galaxies are the most numerous class of galaxies in the cosmos. They cluster around larger galaxies as satellites, some of them on infall trajectories that will eventually see them consumed by their host. The Milky Way has several dozen such satellites, including the large and small Magellanic Clouds. Andromeda has its own collection, and IC 1101 is surrounded by the remnants and partial remnants of the hundreds of galaxies it has consumed over its lifetime. In the middle of the size distribution sit the spiral galaxies, including the Milky Way and Andromeda, and a range of elliptical galaxies of various masses. These are the objects that fill most of the pages of introductory astronomy textbooks. The galaxies that were discovered in the 1920s and 1930s, when Edwin Hubble was systematically measuring the distances to what had previously been called nebulae, and establishing that the universe was far larger than anyone had imagined. Hubble's discovery was itself one of the most significant scientific revelations in human history. Before his work in the 1920s, the prevailing view among astronomers was that the entire observable universe consisted of the Milky Way and its immediate surroundings. The debate over whether certain fuzzy nebulae were objects within the Milky Way or independent stellar systems beyond it was known as the Great Debate, and it was formally contested between Heber Curtis and Harlow Shapley in 1920. Curtis argued that the spiral nebulae were island universes, external galaxies far beyond our own. Shapley argued that they were structures within or very near the Milky Way. Hubble settled the debate in 1924 by measuring the distance to the Andromeda Nebula using variable stars called Cepheids, whose intrinsic luminosity is directly related to their pulsation period. His measurement placed Andromeda at roughly 900,000 light-years, far beyond the boundaries of the Milky Way as then understood. The universe was suddenly revealed to be incomparably larger than any previous estimate, filled not with one galaxy, but with a practically infinite number of them. Almost overnight, the known universe expanded by a factor of millions. And since Hubble, each generation of more powerful telescopes has continued to push the observable frontier further outward. The Hubble Space Telescope, launched in 1990, provided the deepest views of the universe ever achieved at the time, revealing thousands of galaxies in regions of sky that appeared empty to ground-based telescopes. The Hubble Ultra Deep Field, a long-exposure image of a patch of sky only about 1/13 the diameter of the full moon, contains approximately 10,000 galaxies, each of them a collection of billions to trillions of stars, each separated from its neighbors by millions of light-years. The James Webb Space Telescope, which began science operations in 2022, pushed further still, observing galaxies that formed within the first few 100 million years after the Big Bang. The earliest galaxies Webb has identified are seen as they appeared when the universe was only about 300 million years old, less than 3% of its current age. These early galaxies were different from the ones we see nearby today. Many were irregular, compact, and extraordinarily active, producing stars at rates per unit mass that exceed anything observed in the modern universe. The transition from those early, irregular, intensely star-forming systems to the ordered spirals and massive ellipticals of the modern universe took billions of years and involved countless mergers, interactions, and feedback processes. The story of how the early universe's small, irregular galaxies became the large, mature systems we observe today is one of the central narratives of modern astrophysics. And IC 1101 represents the extreme end product of that story, the final form of a galaxy that has had the maximum possible time and the maximum possible supply of infalling material to grow. Understanding this history also means understanding the role that cosmic time plays in galactic growth. Galaxies in the early universe were much more densely packed. The universe was smaller then, meaning the average distance between galaxies was a fraction of what it is today. Galaxy interactions and mergers were correspondingly more frequent. The rate of galactic mergers was highest in the first few billion years after the Big Bang, when the universe was younger and denser, and has been declining ever since, as the expansion of the universe gradually increases the distances between galaxies and reduces the frequency of interactions. This means that the CD galaxies, at the centers of massive clusters, did most of their growing early in cosmic history. They assembled the bulk of their mass through the intense period of mergers that characterized the early universe. When galaxies were falling into cluster centers frequently, and the gravitational potential wells were being rapidly deepened by incoming mass, by the time the universe was several billion years old, the merger rate had slowed substantially, and the central galaxies were already approaching their mature, largely quiescent forms. This is why IC 1101's stellar populations are so old. The stars it contains are predominantly ancient, formed in the galaxies that merged to build it during the universe's early active period. The galaxy consumed so many others so quickly that it consumed most of the available gas that might have fueled ongoing star formation. What remains today is the gravitational legacy of that early activity, an enormous collection of old stars slowly dimming in a galaxy cluster that has largely settled into a state of gravitational equilibrium. The giant radio galaxies tell a somewhat different story about timing. Porphyrion existed when the universe was only 6.3 billion years old, less than half its current age. At that cosmic epoch, the universe was still actively assembling its large-scale structures. Galaxy clusters were denser. The intergalactic medium was richer in gas. Supermassive black holes were more commonly in active, jet-producing phases. The conditions that allow radio jets to grow to extraordinary sizes, a powerful central engine combined with a relatively low-density surrounding medium, were more commonly met during that earlier cosmic epoch. The fact that Porphyrion's jets existed when the universe was relatively young raises interesting questions about whether the current universe, older and less active, can still produce structures of comparable scale. The answer appears to be yes, based on the discovery of Alcyonius, which is a nearby, low redshift object. But the population statistics may differ between the early and modern universe. Whether the most extreme giant radio galaxies preferentially formed at early cosmic epochs or are equally likely to form today is one of the questions the square kilometer array will eventually help resolve. There is also the question of what happens to giant radio structures after the central engine that produced them runs out of fuel. Active galactic nuclei, including the jet-producing black holes that power giant radio galaxies, are not permanently active. They cycle between active and quiescent phases depending on the availability of infalling material. When the accretion rate drops, the jets shut off. The existing radio lobes, no longer being fed by new material from the jets, gradually fade as their electrons lose energy and the synchrotron radiation they emit diminishes. This means that the giant radio structures we observe represent only the currently active or recently active population of objects. For every giant radio galaxy with visible lobes, there may be many more that were once equally large or larger, whose lobes have since faded below detection thresholds. The total number of giant radio structures that have existed over cosmic history, including those that have now faded, could be far greater than current observations suggest. This is one of the reasons astronomers believe the cosmic web may be far more magnetically structured than previously understood. Even after the visible radio lobes fade, the magnetic fields they deposited in the intergalactic medium persist. The magnetized plasma injected by millions of radio jets over cosmic time may have been responsible for seeding the magnetic fields that permeate the intergalactic medium today. The universe we inhabit may be threaded with the invisible, magnetic legacy of billions of past galactic outflows, each one a faded giant radio galaxy, whose jets have long since ceased, but whose magnetic footprint remains woven into the fabric of intergalactic space. The connection between supermassive black holes and their host galaxies, and between those galaxies and the large-scale structure of the universe, is one of the most actively studied areas in modern astrophysics. For years, astronomers were puzzled by what is sometimes called the galaxy black hole coevolution problem. Observations revealed a surprisingly tight relationship between the mass of a galaxy's central supermassive black hole and the properties of the galaxy's stellar bulge, particularly the velocity dispersion of the stars in the bulge. Larger black holes tended to live in bulges with faster-moving stars, and the relationship was remarkably consistent across galaxies, spanning many orders of magnitude in mass. The existence of this tight relationship was unexpected because the supermassive black hole occupies a region many orders of magnitude smaller than the galaxy's bulge. There should be no obvious reason why a black hole confined to the innermost fraction of a light year should know anything about the stars orbiting at radii of thousands of light years. The relationship implies that the black hole and the galaxy influenced each other's growth in a self-regulating feedback loop that operated over billions of years. The leading explanation involves the very jets and outflows that produce giant radio structures. When the black hole is actively accreting material and producing jets, the energy deposited into the galaxy's interstellar medium can heat and expel the gas that would otherwise form new stars, suppressing star formation and limiting how much material remains available to feed the black hole itself. This feedback mechanism couples the growth of the black hole to the growth of the galaxy, ensuring that neither can grow without limushed, independently of the other. The galaxy regulates the black hole, and the black hole regulates the galaxy. In the most massive galaxies at the centers of rich clusters, this feedback operates not just on the galaxy itself, but on the hot intracluster gas surrounding it. The jets and bubbles of radioplasma pumped into the cluster environment by the central black hole provide a heating source that prevents the hot gas from cooling and flowing inward to fuel excessive star formation. Without this heating, simulations predict that the most massive galaxy clusters should have produced far more stars than they actually contain. The black hole's energy output, channeled through jets and radio lobes, is what keeps the cluster's hot gas from cooling too rapidly, maintaining the thermal balance of the cluster environment over billions of years. This process, called AGN feedback, where AGN stands for active galactic nucleus, is now understood to be one of the primary regulators of galaxy formation in the universe. It is the reason that galaxies above a certain mass threshold tend to be red, old, and star formation quenched, rather than blue, young, and star forming. The most massive black holes in the most massive galaxies are the most efficient suppressors of star formation, which is why the largest galaxies tend to be the oldest and reddest. IC 1101's black hole, weighing somewhere between 40 billion and 100 billion solar masses, was one of the most powerful AGN feedback sources in its cluster during its active phase. When it was accreting material at high rates, billions of years ago, the energy it deposited into the surrounding intracluster medium through jets and outflows may have been responsible for shaping the stellar properties of galaxies throughout the Abell 2029 cluster. The stars that formed, and those that did not form, across hundreds of thousands of light years of cluster space, were all influenced by the activity of a black hole sitting at the center of what would become the largest visible galaxy ever observed. The connection runs in both directions. The galaxy shaped the black hole through mergers that brought additional black hole mass from consumed galaxies. And the black hole shaped the galaxy through jets that regulated star formation and heated the gas supply. The final product, the massive, quiescent, slowly dimming galaxy we observe today, is the result of this billions of years conversation between a growing galaxy and its growing central engine. Now consider one more layer of this picture, because the story of the largest galaxies is also the story of dark matter, the invisible component that makes up the majority of every galaxy's mass and the backbone of every large-scale structure in the universe. Dark matter does not emit, absorb, or reflect light. It interacts with ordinary matter only through gravity. It cannot be directly observed. Its existence was inferred from the gravitational effects it produces on ordinary matter, beginning with the observations of Fritz Zwicky in the 1930s, who noticed that galaxies in the Coma cluster were moving too fast to be held together by the visible mass of the cluster, and continuing through the landmark rotational velocity measurements of Vera Rubin in the 1970s, who demonstrated that stars in the outer regions of spiral galaxies orbit at the same speed as stars near the center, contrary to the expectations of Newtonian dynamics for a mass distribution concentrated in the visible disk. The only explanation consistent with these observations is that galaxies are embedded in vast halos of unseen matter extending far beyond their visible stellar bodies. These dark matter halos contribute the majority of a galaxy's total gravitational mass. The Milky Way's visible stars represent perhaps 5 to 10% of the total mass of the system. The rest is dark matter, distributed in a roughly spherical halo extending far beyond the stellar disk. For IC 1101, the dark matter halo extends even further than the stellar halo, reaching out into the surrounding galaxy cluster. The galaxy's total gravitational mass, including dark matter, is vastly greater than what the visible stars alone would suggest. When astronomers measure galaxy sizes using gravitational lensing, which measures how the galaxy's mass bends the light of background objects, they detect mass extending to radii far greater than any optical observation of the stellar body would imply. The same is true of galaxy clusters. The dark matter halos of galaxy clusters extend over scales of several megaparsecs, with roughly 80 to 90% of the total cluster mass in dark matter, rather than in stars or hot gas. The visible galaxies within a cluster are like luminous signposts embedded in a vast, invisible cloud of dark matter that provides the gravitational scaffolding for the entire structure. Understanding the full extent of IC 1101 therefore means accounting for its dark matter halo, which extends further than any stellar observation can directly probe. The visible stellar body and diffuse stellar halo that astronomers can observe represent only the luminous tip of a gravitational structure that encompasses the entire cluster. In this sense, the question of where IC 1101 ends is not just ambiguous because of intracluster light. It is ambiguous because the galaxy's gravitational influence, carried primarily by dark matter, extends to scales that blur into the cluster's own dark matter halo, which in turn blurs into the surrounding filaments of the cosmic web. There is no clean edge. There is only a gradient from the dense bright stellar core at the center, outward through the stellar body, through the diffuse stellar halo, into the intracluster light, and then into the dark matter halo that extends to scales approaching the cluster radius, and then into the dark matter filaments of the cosmic web beyond. At every scale, the galaxy is present, its gravitational influence operating, its history written in the distribution of matter around it. This is the most fundamental reason why the question of the largest galaxy cannot be answered cleanly. Not just because radiolobes complicate the definition, not just because halos fade without clear edges, but because the gravitational structures of the largest galaxies are embedded in and connected to the gravitational structures of the universe at every scale. Drawing a boundary around IC 1101 means choosing an arbitrary radius at which to stop counting. Any such choice is a human decision, not a physical one. The universe does not organize itself into discrete objects. It organizes itself into overlapping zones of influence, each nested within larger zones, connected through gravity and thermodynamics in a hierarchy that extends from individual stars up to the observable universe itself. Galaxies are concentrations in this hierarchy, regions where the matter density is high enough that the structures are interesting and distinct from their surroundings. But they are not discrete. They are nodes in a network, and the network has no obvious fundamental unit. If you want to understand something about human cognition, as well as about the cosmos, study the history of how scientists have tried to define exactly where one galaxy ends and another begins. The problem is not one of insufficient data or inadequate instruments. It is a problem of ontology, of what kind of object a galaxy actually is. And the answer, the more carefully you look, is that a galaxy is not quite the kind of thing that has a definite extent. It is a pattern, a concentration, a region of elevated density in a continuous distribution of matter. And concentrations, unlike solid objects, do not have edges. The stars in IC 1101 do not know they are inside a galaxy. The dark matter particles in its halo do not know they are in the halo. The electrons in Porphyrion's radiolobes do not know they are part of a galactic structure. These are categories we impose on the universe to make it legible, and they are useful categories. But at the extremes, where the most massive galaxies sit embedded in the most massive clusters, connected to the large-scale structure through filaments of dark matter, the categories begin to show their seams. And this is, in the end, the deepest lesson in the story of the largest galaxy ever found. It is not a lesson about which specific object holds the record. Records will be broken, instruments will improve, new objects will be discovered that surpass everything in current catalogs. The question of whether IC 1101 or Porphyrion or some as yet unknown structure deserves the title of largest galaxy will be debated and revised for years to come. The deeper lesson is about the nature of size itself when applied to structures that exist at the boundary between galaxies and the cosmos. When we ask how big the largest galaxy is, we are asking a question that seems precise, but is actually asking us to make choices that the universe itself has not made. Where does the galaxy end? Where does the halo become intracluster light? Where does the radiolobe stop being part of the galaxy and start being part of the intergalactic medium? The universe presents us with continuous gradients and asks us to draw lines. And no matter where we draw them, the result depends on where we chose to look. There is something clarifying about this, if you approach it in the right spirit. The fact that the largest galaxy cannot be precisely defined is not a failure of astronomy. It is a success of understanding. It means that astronomers have looked carefully enough at the structure of the cosmos to see past the simplified categories that once seemed sufficient. Galaxies were originally defined as collections of stars held together by gravity. And that definition worked fine when the objects being classified were ordinary spirals and ellipticals seen from a distance. But when you examine the largest systems closely enough, when you trace their halos to their faintest extensions and measure the radio emission from their jets to its most distant reaches, you find that the simple definition no longer captures what is actually there. What is actually there is something more complex and more interesting, a gravitational hierarchy in which the largest galaxies are not contained objects, but active participants in the large-scale organization of matter in the universe. IC 1101 is not just sitting inside Able 2029, it is shaping Able 2029, consuming its galaxies, heating its gas, establishing its thermal properties through its past black hole activity. Porphyrion is not just sitting inside the cosmic web. It is touching the cosmic web, magnetizing it, heating the intergalactic medium that fills the voids between filaments. potentially influencing the formation of future galaxies in filaments millions of light years away from its central engine. These are not passive objects floating in an indifferent cosmos. They are the universe's most active agents of structural organization at the galactic and cosmological scales. The places where the physics of black hole accretion meets the physics of large-scale structure formation, where the smallest scales of quantum fluctuation have been amplified through billions of years of gravitational evolution into structures that interact with the cosmos itself. And here, finally, is the number that summarizes everything. Not the size of IC 1101's halo, not the extent of Porphyrion's jets, not the ratio of Alcyoneus to the Milky Way. The number is this. The universe is approximately 93 billion light-years in diameter, as currently observable, and it may be vastly larger beyond the observational horizon. Within that 93 billion light-year sphere, there are approximately 2 trillion galaxies. Most of them are dwarfs. A small fraction are spirals, like the Milky Way. A tiny fraction are massive ellipticals. An even tinier fraction are CD giants, like IC 1101. And an extremely small, but now well-documented population produce giant radio structures like those of Alcyoneus and Porphyrion. We have characterized perhaps a fraction of a percent of those 2 trillion galaxies in any detail. We have measured the sizes, masses, and structural properties of a few 100,000 at most. The universe's full inventory of its largest structures has not yet been taken. The data needed to establish the true upper end of the galaxy size distribution does not yet exist. It is waiting in the unobserved sky, encoded in radio photons that have been traveling through intergalactic space for billions of years and have not yet reached any antenna we have built. Whatever that data contains, whatever records it will establish and re-establish as surveys improve and instruments grow more sensitive, one thing is already clear from what we do know. The universe's capacity for building large structures exceeds our current ability to characterize it. The ladder of cosmic scale extends upward past the altitude where human intuition can breathe, and the structures at the top of that ladder, IC 1101, and Alcyoneus and Porphyrion, and whatever lies beyond them in the unobserved sky, are not just impressive objects at the extreme end of a size distribution. They are evidence that the cosmos builds without limit, that gravity given enough time and material produces structures at every scale it has access to, and that the scales it has access to extend from the subatomic to the cosmological without any obvious discontinuity. The largest galaxy we have ever found is a reminder that the universe was not built to any human specification. It was not designed to be comprehensible or bounded or neatly categorized. It was built by physics, operating over billions of years, without any awareness of the cognitive limitations of the species that would one day try to measure it. And the structures it has built are not large by human standards. They are large by cosmic standards. They are large in a way that makes human standards irrelevant. In encountering that irrelevance, following the ladder up until the rungs become too distant to see, and then looking down and realizing how small the starting point was, is one of the most genuinely educational things that astronomy can do for a curious mind. The records will keep falling. The instruments will keep improving. And the cosmos, indifferent to our categories and our records and our need for clean answers, will keep building. One aspect of this story that deserves more attention is the question of how we actually measure these objects across the vast distances separating us from them, because the measurements themselves reveal something important about the limits and capabilities of observational astronomy. When an astronomer says that IC 1101 has a stellar halo extending 2 million light-years in radius, or that Porphyrion's jets span 23 million light-years, those numbers did not come from direct physical measurement in any conventional sense. They came from a chain of inference that depends on a deep and carefully constructed framework for understanding cosmic distances. The most fundamental challenge in measuring any galaxy is determining how far away it is. Without knowing the distance, you cannot convert the angular size of a galaxy on the sky into a physical size. A galaxy that appears large in a telescope image might be nearby and modest in physical scale, or it might be distant and enormous. Distinguishing between these possibilities requires an independent measurement of distance. Astronomers have developed a hierarchy of techniques for measuring cosmic distances, collectively called the cosmic distance ladder. At the bottom of the ladder are the most direct methods, which work only for nearby objects. Stellar parallax measures the slight apparent shift in a star's position against the background of more distant stars as Earth orbits the Sun, allowing direct geometric measurement of distances out to a few thousand light-years. Standard candles, objects whose intrinsic luminosity is known from theory or calibration, allow distances to be inferred from apparent brightness. The dimmer the object appears, the further away it must be, assuming you know how intrinsically bright it is. Edwin Hubble used Cepheid variable stars as standard candles in the 1920s. Cepheids pulsate with a period directly related to their intrinsic luminosity, a relationship discovered by Henrietta Swan Leavitt in 1912. By measuring how long a Cepheid takes to complete one pulsation cycle, you can calculate how intrinsically bright it is. Comparing that to how bright it appears from Earth gives the distance. This technique allowed Hubble to establish that Andromeda was far beyond the Milky Way. For more distant galaxies, Cepheids become too faint to resolve individually, and astronomers must use brighter standard candles. Type Ia supernovae, the thermonuclear explosions of white dwarf stars that have exceeded a critical mass threshold, produce luminosities so extreme that they can be observed across billions of light-years. And because they result from a consistent physical process, they produce a fairly predictable peak luminosity that can be calibrated against closer distance measurements. Type Ia supernovae were used in the late 1990s to make the landmark discovery that the expansion of the universe is accelerating, a finding that earned the Nobel Prize in Physics in 2011 and established dark energy as a necessary component of cosmological models. For very distant galaxies, like IC 1101 and the host galaxies of Alcyonius and Porphyrion, astronomers primarily rely on a measurement called redshift. When a galaxy is moving away from us, the light it emits is stretched to longer wavelengths by the expansion of space between us and the galaxy. This stretching is called redshift, measured as the fractional change in the observed wavelength of known spectral features. The amount of redshift is directly related to how far the light has traveled through the expanding universe, which is directly related to how long ago the light was emitted, which can be converted to a physical distance using our best models of the universe's expansion history. IC 1101 has a redshift of approximately 0.077, which corresponds to a distance of roughly 1.15 billion light-years. This is in the regime where the relationship between redshift and distance is well understood, and the measurement is highly reliable. Alcyonius has a lower redshift, making it a nearby, modern universe object. Porphyrion has a higher redshift of about 0.9, placing it at 7.5 billion light-years, in the era when the universe was approximately half its current age. The fact that these distance measurements rely on physical models rather than direct geometric measurement means that they carry uncertainties that reflect our knowledge of cosmological parameters. But for the objects discussed in this story, the uncertainties in distance are relatively small compared to the sizes of the structures involved. The conclusion that Porphyrion's jets span 23 million light-years is not sensitive to the exact value of the Hubble constant within its measured range. The structure is enormous, regardless of which current cosmological measurement you prefer. Once the distance is known, converting angular size on the sky to physical size is straightforward geometry. A structure that subtends a certain angle in the sky at a known distance occupies a physical region of corresponding size. The reported sizes of these galaxies and their associated radio structures are therefore well-determined quantities, not rough estimates, even though they come from indirect measurement chains. The observations of IC 1101 have been made with multiple instruments at multiple wavelengths, and the measurements are consistent across them. Optical and near-infrared imaging from ground-based and space-based telescopes resolve the stellar body and measure its brightness profile. X-ray observations from missions like Chandra and XMM Newton reveal the hot gas surrounding the galaxy and measure the cluster properties. Radio observations resolve the jets and any extended radio emission, and spectroscopic measurements of the stellar velocities in the galaxy's core constrain the mass of the central black hole through the dynamics of the stars orbiting within its gravitational influence. For the giant radio galaxies, the primary measurements come from radio interferometry. An interferometer combines the signals from multiple antennas separated by large distances to achieve an effective angular resolution equivalent to a telescope as large as the separation between the most widely spaced antennas. LOFAR, with its stations spread across European nations, achieves angular resolution sufficient to map the detailed structure of radio lobes extending millions of light-years, even for objects billions of light-years away. The discovery of Alcyonius and the identification of porphyrion both relied on LOFAR's ability to detect very faint, very extended radio emission that would be invisible to instruments with lower sensitivity or coarser resolution. The measurement of porphyrion's jet power and physical extent required not just detecting the radio emission, but modeling the physical properties of the plasma in the lobes. By fitting models of synchrotron emission to the observed radio spectrum and surface brightness distribution, astronomers can infer the density of relativistic electrons, the strength of the magnetic field, and the pressure of the plasma in the lobes. These physical parameters, combined with the observed size and the estimated age of the structure based on the energy losses of the electrons, allow estimates of the total kinetic power being carried by the jets. The result is a picture of the central engine that is surprisingly complete, given that the engine itself is spatially unresolved at the distances involved. This brings up one more remarkable fact about these observations. When we observe porphyrion's jets, we are not looking at a structure that exists right now. We are looking at a structure as it appeared 7.5 billion years ago, when the universe was barely past the midpoint of its current age. The jets we observe may have long since faded. The host galaxy may have evolved substantially. The radio lobes may have expanded further, or dissipated entirely over the 7.5 billion years since the light we observe left the source. What we see is a snapshot in time, not a current state. The same is true of IC 1101, whose light left it over a billion years ago, and of every other galaxy and cosmic structure we observe. Because light travels at a finite speed, and because the cosmos is so vast, every observation we make is an observation of the past. The deeper we look into the universe, the further back in time we see. The most distant galaxies observed by the James Webb Space Telescope are seen as they appeared less than 400 million years after the Big Bang. Looking at them is, in a real and direct sense, looking back in time more than 13 billion years. This means that our picture of the universe is necessarily a composite of observations made at different epochs. Nearby galaxies are seen as they are now. Distant galaxies are seen as they were billions of years ago. We cannot observe a consistent snapshot of the universe as it exists at this moment, because the light from distant regions has been traveling toward us for so long that those regions have evolved substantially since the light departed. The universe we can observe is not the universe as it is, but the universe as it was at different points in its history, with the most distant regions representing the most ancient states. This temporal layering of observations is simultaneously a limitation and an extraordinary opportunity. It is a limitation because it means we cannot directly observe the current state of any object beyond our immediate cosmic neighborhood. But it is an opportunity because it means that by observing at different distances, we can directly trace the evolution of the universe over billions of years. We can observe galaxies in their infancy, billions of light years away, and compare them to mature galaxies nearby. We can watch the growth of large-scale structure by comparing the distribution of galaxies at different cosmic epochs. We can measure how the universe's star formation rate, its galaxy merger rate, and its supermassive black hole activity have all evolved over the history of the cosmos. The study of giant radio galaxies benefits directly from this temporal depth. By comparing the population of giant radio galaxies at different redshifts, astronomers can trace how the jet production efficiency of black holes has changed over cosmic time, how the properties of the intergalactic medium have evolved, and how the maximum size of radio structures has changed as the universe has expanded and its mean density has decreased. This kind of comparative evolutionary study is possible only because the universe is so large that looking far away means looking far back in time. Every photon that reaches our telescopes from a distant galaxy is a message from the past, carrying information about the state of the universe at the moment of its emission. The photons from IC 1101 carry information about a galaxy that was already ancient when they left. The photons from porphyrion carry information about a jet system that existed in a younger, denser universe than the one we inhabit today. And the photons we have not yet collected, those still traveling toward us from the most distant and the most extreme structures in the observable universe, carry information about the earliest epoch of galaxy formation, when the universe was just beginning to assemble the structures that would eventually produce galaxies like the ones at the center of this story. That is the full scope of what the question of the largest galaxy encompasses. Not just a record to be broken or a number to be cited, but a window into the physics of the universe at every scale. From the quantum fluctuations of the early universe to the formation of the cosmic web, from the accretion of gas onto a black hole, to the injection of magnetized plasma into intergalactic space across tens of millions of light years. The largest galaxies are not just big, they are the universe's most legible signature, written in starlight and radio waves, of what happens when the physics of gravity and thermodynamics operate without constraint over billions of years of cosmic time. Consider too what the story reveals about the practice of science itself. The fact that Alcyonius was discovered in 2022, that Porphyrion followed in 2024, and that a new record holder appeared within months of Porphyrion's announcement is not a sign that previous astronomers were careless or that their instruments were inadequate. It is a sign that the sensitivity required to detect these structures was only recently achieved, and that once achieved, it immediately revealed a population of objects that had been present in the universe all along, waiting for instruments capable of seeing them. LOFAR represents a qualitative leap in the ability to detect faint, extended radio emission. Its sensitivity to diffuse low-frequency radio sources exceeds that of previous radio surveys by an order of magnitude or more in the relevant parameter space. And its initial partial coverage of the sky has already transformed our understanding of the population of giant radio galaxies. This pattern, where a new instrument with capabilities qualitatively different from its predecessors opens a new observational window and immediately reveals unexpected populations of objects, has repeated itself throughout the history of astronomy. When the first X-ray telescopes went into orbit in the 1970s, they revealed a sky populated with X-ray sources that were entirely invisible to optical instruments. Sources corresponding to neutron stars in binary systems, active galactic nuclei, galaxy clusters filled with superheated gas, and the remnants of stellar explosions. When infrared astronomy matured, it revealed dusty regions of active star formation hidden behind clouds that block visible light. When gravitational wave detectors achieved sufficient sensitivity in 2015, they immediately detected merging black holes, confirming in a single observation both the existence of binary black hole systems and the validity of general relativity in the strong field limit. Each new observational capability has expanded the catalog of known phenomena and required updates to theoretical models. The Square Kilometer Array will do the same for the radio universe, and whatever it finds, whatever records it establishes, whatever new categories of objects it reveals, will require the same process of conceptual revision that has accompanied every major advance in astronomical instrumentation. The universe has consistently proven to contain more than our models predicted, and the pattern of discovery suggests that this will continue as long as we build instruments with the sensitivity to see further and fainter than before. The largest galaxy we have ever found, whatever it is at any given moment in the history of astronomical discovery, is therefore not just an object. It is a benchmark for our current observational reach, a marker of how far our instruments can see and how sensitive they have become. When the record changes, it is not just a new galaxy that has been found. It is evidence that our window onto the cosmos has expanded, that the darkness has retreated a little further, and that the universe has revealed another piece of itself to the curious species that has spent the past 4 centuries building telescopes and pointing them at the sky. And for anyone who has followed the full arc of this story, from the Milky Way outward, through Andromeda and IC, 1101, and Alcyonius and Porphyrion, and up through the physics of jets and dark matter halos, and cosmic web filaments and observational cosmology, the thing to carry away is not the specific numbers. Numbers change as measurements improve. The thing to carry away is the shape of the story itself. The recognition that the universe builds without evident limit, that every scale of structure we have ever found has been nested within a larger scale, and that the boundary between what a galaxy is and what the cosmos is turns out to be a question that the universe itself has never answered and may never need to. The history of every major astronomical discovery is ultimately the history of an instrument that let us see something we could not see before. And when that something turns out to be larger, more complex, and more consequential than the models predicted, the right response is not to feel overwhelmed by the numbers. The right response is to update the models, build the next instrument, and look again with clearer eyes. That is exactly what the community studying the largest galaxies is doing right now. The records will continue to fall. The understanding will continue to deepen, and the universe will continue, as it always has, to exceed every expectation we bring to it. The cosmos has no interest in remaining at the edge of what we can imagine. It simply continues, as it always has, building structures we have not yet conceived, in regions we have not yet observed, at scales we have not yet measured. That is the final and most important fact about the largest galaxy we have ever found. Thanks for watching till the end. We'll see you in the next one.